So hello everyone, I'm Fei Li, or you can call me Dennis. And today I'm going to talk about our paper, Photon-Driven Manifold Sampling. So let's first start with the context. So the topic we are focusing on is caustic sampling, or more specifically is the multi-bounce caustic. And sampling these caustic is hard, especially for like a method that utilize random sampling like path tracing. And it is because it's like playing the lottery at each bounce, where only a few directions on the entire hemisphere will have the actual contribution, and this normally results in high variance in final image. So many power works will rely on specially designed techniques like manifold walk. And so now let's talk about what is manifold walk here. So it is originally proposed as a mutation strategy for metropolis light transport. But later works found out that, we can actually use manifold walk to find new valid specular path, which we will call an admissible path later on. And all we need to do is just to give it the manifold walk process a C path, which contains a general guess to where these specular interactions are. And the manifold walk process will find their exact location for us. So this leads to an interesting behavior called basin of convergence, where many different C paths may lead to the same admissible path after applying the manifold walk. So now we are trying to find these basins instead of those few directions that we want to find. So this makes sampling these caustic a lot more easier. So the first to utilize this property of finding the specular path is manifold next event estimation. They initialize their C path by connecting the last vertex to the light source. And this allows them to efficiently sample refractive caustic, but they cannot handle reflective caustic well, and they can only find one solution even if multiple exists. So later on, spectral manifold sampling trying to resolve all MNE's problem by introducing random sampling into their process. So they uniformly sample spectral vertex from all specular surface in the scenes to serve as the C path vertex, which allow them to find all potential solutions but introduce a lot of variance into the final image. So to combat this variance problem, many works try to improve SMS in two aspects. The first is by improving the manifold walk process itself, enhancing exploration strength, like specular manifold bisection sampling here. They introduce a large jump into the manifold walk process itself, allowing more admissible paths to be found and avoid getting stuck on local extreme when they do the exploration. And then another branch is to importance sampling according to converged basin, which they improve the success rate for manifold walk to find admissible path by giving it a better C path. So the first one is manifold path guiding, which use path guiding techniques to guide their C path direction with a learned distribution from training samples. And the second one is spatial temporal admissible path reuse. They share and reuse the neighboring pixel's admissible path as the C path of the current pixel. This one actually shares many similarities to our methods. And the final one is the neural path sampling, which is very similar to manifold path guiding, but they use a neural network to predict the C path directions. And finally, our method, photon-driven manifold sampling, also lies in the second category of using importance sampling to find the C path. So our method is based around three key observations we made from all the previous works. The first is the lack of bidirectional informations. So all the methods we mentioned before use unidirectional exploration starting from the shading points. But from previous experience, we know that bidirectional methods like bidirectional path tracing or photon mapping are more suitable for sampling caustic path. So in our method, we just decided to use photon as our source of bidirectional information, which gave us the general location or direction of where these specular paths are coming from. And the second observation is the similarity in neighboring area. If we visualize the basin of convergence in neighboring area like here, with two shading points A and B, you can see that they share very similar converged basin in terms of location and distribution. So we can say that admissible path in B are most likely also lies in the A's converged basin, which leads to a valid path which we want. So this oh, sorry, I skipped it. So this is also the property that spatial temporal emissive path reuse we mentioned before are exploiting. So this also gives us the reason to utilize photon paths that are nearby to our shading points. And finally, the final observation is the more random sampling leads to variance. This is related to the first observation, as all methods use unidirectional exploration. So when they generate their C path, they have no idea that where is the caustic is coming from, or how many bounds this caustic should have, or even what type of interaction is caused by reflection or refraction. They have no idea. So they have to use random sampling, or in other words, guessing the answer for all these questions. So instead of guessing, our method just take the answer from nearby photons. We reuse all path vertices from the photons to form our C path. And thus allow us to achieve lower variance compared to other methods.
All right.
So we just go through the main idea of our method, and now let's go through the details. We use two-pass approach, as we need dedicated paths to generate the photons. And so let's start from the photon pass.
Okay, I'll just put on your t-shirt if that's okay.
So the main goal of this photon pass is to collect caustic photons, as we don't need photons that have no spectral interactions. They have no use to the manifold process.
Okay.
So we sample the first photon vertex similar to how SMS sample their C path. We sample them directly on the spectral surface, and then we trace towards them, like this. And this allows us to have higher chance to generate caustic photons. And after that, we just keep tracing until the photon first hit a diffuse surface, and then we store the path vertices, which we will use for future reuse. So after that's all for the photon pass. So after that, we already got all the caustic photon we need. So now it's the I-pass turn. So the first question in I-pass will be, how do we select photons? Because we have so many we just collected, and which one is more important to us with the current shading points? So generally, people might say maybe the closer is the better photons. Like in photon mapping, in some works, they will give the closer photon higher weight or higher contribution. But here we found out that it is not always the case if we apply manifold walk later on. For example, with photon here also is A and B, we might choose B because it is closer to the shading point. But if we visualize the incoming direction, you will see that A is actually more similar to the direction that shading point should have. So in this case, A is actually more optimal choice for manifold walk process, as a smaller mutation is needed. But if we force it to choose B, which is the closest one, we actually got these weird artifacts to emerge. And it is because the closer are not guaranteed to lie inside the converged basin of our current pixels, current shading point. And this is most often happen around the edge of caustics. So we just employ a very simple algorithm to sidestep this problem, linear search with the update probability. So basically, we go through all the photons and have a chance to update the selected photon when encounter a closer photon. And if we set the update probability to 1, it will equivalent to just selecting the closest photon. But if we set it to lower value, it will perform more uniformly selection. And in the end, we just set it to 0.25, which allow all photons still have a chance to be selected, but closer photons still will have a higher chance. And so now we have select the photon. So the next stage is to reuse them. As previously mentioned, we will reuse all the photon vertices. And the first step is to reuse. First time to reuse is to we connect the shading point to the last specular vertex of the photon path. And then we will follow the photon path before reaching the light vertex. And then we will replace the photon light vertex with the newly sampled vertex on the same light source. And now we will have a complete C path for us to apply the manifold walk. And you might ask why we want to replace the old light vertex. It is because if we not, we are basically sample caustic from a bunch of virtual point lights. And this will cause these pattern or artifacts to emerge. And they are very hard to converge, require many sample or photons to do it. So we just replace it to better account for area lights. Another problem is when photon count is low, there may exist many gaps between different photons. And these gaps might make us miss some chance to find potential admissible path in the path space. So we introduce a small perturbation method by setting a maximum perturbation angle, theta. And we will randomly sample a new direction inside this angle. And because it's like a cone, so we call this method just photon cone, perturbation cone. And if we do this at each bounce, then we will get a slightly offset C path, which allows us to explore the local path space even more thoroughly. But be careful with how you set up the theta value, because generally smaller theta is more suitable for higher photon counts, as their gaps should be smaller because we have more photons. And lower photon counts should require wider cones or higher theta value. But at the same time, wider cone will also come with higher variance, as we are basically reintroducing the random sampling into our methods. And after that, our CPAT is finally ready for manifold walk process. And our method basically follows the same steps as the original SMS after this. So we will feed the CPath into the manifold walk to find the admissible path if it exists. And then evaluate their PDF using the binary trials. And finally, we will calculate the path contribution to the final image. So now let's see some results. All the image show later on is rendered with 2 minutes on the same CPUs for equal time comparisons. This is playing. Oh yeah, it's playing. So as you can see here, our method is more efficient at sampling multi-bounce caustic compared to the original SMS. And we can also achieve significant variance reduction. Sorry, it's out of sync. Yeah, great. And if we compare to other methods that build upon SMS, like manifold bisection sampling, manifold path guiding, to our method, we also can achieve the lowest MSE value in the scene. And if we look at the performance side, many other SMS methods that based on SMS will encounter a performance problem when we try to sample longer specular chains. Like here with the specular bisection sampling, they can only achieve 3 samples per pixel with 2 minutes. And our method can still achieve 19 samples per pixel in the scene with maximum length to 4 bounce caustic. And in this swimming pool scene, this actually showcases one of our weak points with this method. Because this thing is illuminated with an environment map, which we can see the environment map as a very large light source. And in our light substitution pass, we have a chance to sample a light vertex that is very far away from the original, which make the manifold walk process have a higher chance to fail. And on the other hand, the bisection sampling method, because they introduced a large jump into their manifold walk, they can use the large jump to find this difficult path more easily. So in this case, they have the lowest MSE in the scene, and we still can achieve the second place. And we also conduct experiment with photon mapping. Here is the progressive photon mapping and photon mapping. The main advantage of our method over these 2 methods is that because we can extrapolate spectral path from existing spectral path using manifold walk, we can get a very sharp image using significantly less photons. So as you can see here, if we limited the used photon count to only 10,000 with original photon maps, the results still very blurry, and while our method can achieve very sharp caustic details. So in conclusion, we introduce an effective and unbiased method for multi-bounce Causic sampling by introducing a bidirectional CPath sampling strategy. Accompanying that, we also introduce an efficient way to sample Causic photons and a photon-reduced scheme for manifold walk process. And that's it for my presentation. Thank you.
So time for Q&A. Any questions?
Yes.
We have just one mic, so could you shout?
Okay. You mean? Okay, screens.
So the question is how to compare with previous reuse approaches.
Okay. Yeah. I have to repeat the question, or it's fine.
You can.
Okay. Yeah. So your question is, how does this method compare to the screen space? Like, I think it's the admissible path reuse one, yes, or the other one? Okay. Mainly is how they find their CPath, because they reuse the CPath, they reuse the admissible path in screen space, but they still have to find it first. And the advantage of our method is because we sample them from the light source, so we are more easy to find these CPath than theirs. And another thing is that they derive their formulation using the biased SMS process, so their result is biased. Yes, I think this are the main difference. Thank you.
Some other questions?
You compared this on the CPU, right? Is it done on the GPU as well?
Okay, so the question is, we are done this in CPU if there is GPU implementation. Yeah, we are working on it. We have only implemented the manifold next event estimation. We haven't implemented this method on the GPU yet. Yeah, we are trying to do it. Yeah.
Some other questions? So I have one question. What is the you propose new seeding strategy, right? So what is overhead of this seeding compared to the total time?
Total time. Let me think. I think there are two bottlenecks. The one is existing original SMS is the binary trial estimation, because we need to know the path PDF in order for unbiased estimation, but in order to find that, we need to use binary trial, which is basically keep repeating the sampling process until the same path emerge again, and we can evaluate the PDF. That is the old problem for the SMS. Another bottleneck I think will happen with our method is because we currently use linear search to find the photons. So we have to go through all the photons currently. So if our photon count is large, then that will take some time to do it. Yes. And I think that is one of the bottlenecks.
So this is for future work?
Yes, for future work. Okay. Because we are still trying to find a better indication for which photon is better, because currently the distance doesn't work and the throughput might not work. So yeah, that's the current problem.
Yeah, thank you. Some other questions?
Yeah, yes.
Here in two passes, I passes, photon pass, how does it affect CPU usage and memory usage in
Okay, so the problem is that we use two paths, and you are wondering about the
question.
Huh?
Can you repeat the question?
Okay, the problem is we use two paths, and you are wondering about the memory requirement.
Yeah, so memory usage and CPU.
Okay. Because currently we are only, the photon path, we only store the path vertices location, so we didn't store any other. We basically retrace the whole path from in the iPath. We use that to recover the information we did not store in our photon path. So we use this to try to reduce the information store. So currently we set the photon path to maximum of 16 bounds. and each bounce only store basically a vec3 information for the location of the vertex. So yeah, I currently have no, I didn't bring the data for me with how many memory they use. So yeah, that's, hope this answer your question. Yeah.
How does it affect CPU?
How does it affect CPU? How does it affect CPU? How does it? I think I'm not sure actually. Currently, I'm not sure. Yeah, sorry. This. This.
Okay. How do you avoid using useless photons? For example, if the light source is included in a glass, then the photons will be everywhere, and there will be a lot of useless photons. How do you avoid this case?
Sorry, can you say again? I couldn't hear it very clearly.
How do you avoid using useless photons? For example, if the light source is included in a glass ball, then the photons, the caustic photons will be everywhere, like across the whole thing.
Basically, we currently are still using distance as our main indication of if this photon is useful for us. So if we can shoot the photon from light source to near our location, it have a higher chance to be useful in this current shading point. So it have to reach there in order for us to use it. Is that the problem you're asking?
Now, I mean, if the light source is included in a glass ball, then it will generate like every.
I think that the photons are like everywhere. Like with,
Oh.
like,
Yes, that. So you mean the photon distribution?
yes.
When we want to account for the, I guess, the sensor's visibility? You mean this? This is in one of our future works, as we currently does not consider the visibility to our sensor. So we can maybe apply like some previous work like metropolis sampling or guiding the photons to where it is more important areas. But that is this is in our future work. We currently haven't do anything to that. We only use the method to sample caustic photon.
Some other questions? If not, let's thank our speaker again.